Hi, guys. Welcome back. We're going to start taking a look at Chapter 11 on atomic theory. In this video, we'll learn about light for the most part, and Section 11.2, light and energy. Here's the front page for the presentation, Chapter 11, Atomic Theory. You can click on this link. What that will do is take you to a book that you may or may not find helpful, but it's another resource at your disposal if you'd like one. You can go through here, find some different pictures, find some different examples and things like that. So feel free to peruse that if you think that would be valuable to you. Oops. On the very first slide, we're going to take a look at section 11.2, light and energy. This picture represents all of the different kinds of light, or sometimes it's also called electromagnetic radiation, coming to us from outer space. We think of space as being empty. It's anything but. It is absolutely awash in different wavelengths of light, everything from radio waves all the way up to gamma rays. As a rule, we only pay attention to the visible part of the spectrum, but professional astronomers take advantage of many other kinds of light that we usually don't think about. So light is a wave, and the first thing we want to do is think about waves in terms of frequency and wavelength. Let's start with wavelength. You can see that if the distance between one crest and another crest of a wave isn't very long, you have a short wavelength. When the crests are packed in close together, you've got a short wavelength. If you take that wave and stretch it out so that the crests are now farther apart, you've lengthened the wavelength. Frequency is a little bit different. In fact, frequency is almost the opposite. Frequency counts how many crests pass a given point every second. And it turns out that all kinds of light move at the same speed. In physics, we would beat that horse a little more, but since light always moves at the same speed, regardless of its frequency or wavelength, that means you're going to have more wavelengths, more crests, I should say, passing a point when you've got a short wavelength than you do when you've got a longer wavelength. This is kind of like having cars bunched up close together going 50 miles an hour. Here you've got the cars much more spread out going 55 miles an hour. So the number of cars passing under a bridge, say, is higher when you've got cars closer together than when you've got cars spread out, is another way to think of it. So wavelength is pretty straightforward. Here's another way to think of frequency, though. Frequency is how often something happens. And this web page that you can click on does a pretty good job of demonstrating that. You can take a look at one birth, for example. That is quite something. One death. This is the frequency, estimated by the person who drew this comic strip, of birth and death. You can see that births happen more often than deaths, and if you follow that out and draw some fairly logical conclusions, it's just terrifying in my opinion. And then you can look at other ones as well, but that's frequency. So we characterize light in terms of wavelength and frequency. You can see on this end of the spectrum, we've got the longest waves, the crests are spread out, and the lowest frequencies. We also have low energy, and energy is what we're really going to focus on in this chapter. To be quite honest, we're not going to use these words too much after section 2, but we're going to use this idea of energy all chapter long. What you might want to put together is the idea that frequency and energy are the same, right? Frequency and energy are almost interchangeable in this chapter. So what do you take away from this slide? Well, the first thing you have to take away is that although we only think about the universe in terms of visible light, there are in fact 7 kinds of light: radio, microwave, infrared. The visible we're all familiar with, and then ultraviolet, X-ray, and gamma ray. You have to be able to order these from longer wavelength, starting with radio, to shortest wavelength, which is gamma. You have to be able to order these from the lowest frequency, which is radio, to the highest frequency, which is gamma. And you have to understand that radio waves have the least amount of energy and that gamma waves have the most energy. You should also understand that the 3 kinds of light that are to the left of visible, the 3 kinds of light that have shorter wavelengths than visible, are all dangerous. Ultraviolet light is dangerous to living organisms. X-rays and gamma rays are increasingly more and more dangerous to living organisms. You should also understand that things can look differently in different kinds of light and be able to give a couple of examples. So, for example, infrared light is what you and I call heat. When you put your hands up to a fire, or when you feel the warmth coming off of a stove top or out of a toaster, what you're feeling is infrared radiation. Microwave is exactly the kind of energy or light generated by your microwave oven in the kitchen. It's literally making these microwaves. That's why it's got the name microwave oven. Radio is exactly what you tune in on your car radio, right? So these aren't necessarily exotic or new. We just maybe haven't thought of them as being exactly the same as visible light, just a lot longer or a lot shorter. What's really interesting about this is that objects look different depending on the kind of light you look at them with. So on the left side, we have this is a star that blew up about 1,000 years ago. Today we call it the Crab Nebula. And if you were to look at it with an optical telescope, it would look like a gray smudge. But if you looked at it with a really good camera that could take pictures of many different kinds of light, it would look like this. If you look at an X-rays, it looks very, very different. It almost has a donut or torus shape to it. If you look at an infrared, again, heat, it looks different again. And then in radio waves, you say, wait a minute, are you telling me that this cloud of gas and dust is emitting radio waves that I could pick up with my radio in my car? The answer is yeah. You probably couldn't pick them up with the radio in your car because it isn't sensitive enough. But if it was sensitive enough, your radio would pick up all sorts of interesting things around the universe, right? A little closer to home, here is a dandelion on the right side. This is how it looks in visible light. On the left side is the way a dandelion looks in ultraviolet light. And if you know a bit about nature and birds and insects, you've perhaps read that there are animals, other creatures, that see in different wavelengths than you and I do. And so it says, pardon me, to some insects, for example, a dandelion might look like this. To you and me, it looks just yellow. And this is fairly common among flowers. If you find this interesting, go online and type in visible infrared flowers or visible ultraviolet flowers, something like that. The last thing that you need to know in section 11.2 is that our atmosphere does block some kinds of radiation. Yeah. These very long radio waves get blocked. You can see it's very brown here. And if you follow that tan or brown across, that's 100% atmospheric opacity. There's a $10 word that means 100% blocked by the atmosphere. For reasons I don't understand, once you get to this spot right here, all of a sudden the atmosphere opens up and radio waves can pass right through, which means that we can put radio dishes on the surface of the Earth that see some, but not all, radio waves. The infrared spectrum doesn't get through. If you want to look at the universe through infrared, you've got to put the telescope in outer space. There's no other way around it. Visible light, of course, gets through. If it didn't, we wouldn't be able to see anything in visible light. There's just a very small amount of ultraviolet that gets through. We know that must be true because if you're a light-skinned person, you do get a sunburn from the sun. Ultraviolet rays are dangerous to us. And then X-rays, well, I should back up just a bit. Most ultraviolet, all of the X-rays and all of the gamma rays, thank goodness, are blocked by the Earth's atmosphere. If they weren't, I'm going to go out on a limb here. I'm not a biologist, but I'm going to say that pretty much most of the Earth's surface would be sterile if gamma rays and X-rays and all of the ultraviolet light could get through the atmosphere. But it doesn't. So I'll ask you questions about this. What wavelengths of light can get through the Earth's atmosphere and which wavelengths cannot?